Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Our chapter today is Logarithmic Functions Properties. Before we talk about logarithmic functions and its properties, let's remember together antiderivatives. Let x be a non-zero real number and n be any rational number such that n is never negative 1. Well, the integral of xn dx is xn plus 1 over n plus 1 plus c, where c is an arbitrary constant. So, the integral of x to the power n dx is x to the power n plus 1 over n plus 1, and we always add a constant. Let's take some examples. We need to find each of the following antiderivatives. First, the integral of x cubed dx. This is of the form xn dx. So we add 1 to the exponent and then we divide by the sum and we add c. This would be x4 over 4 plus c. The integral of x7 dx. This is x8 over 8 plus c, applying the same property. The integral of t to the power negative 3 dt. This is t to the power negative 2 over negative 2 plus c. We also apply the same property. The integral of u negative 5 du. This is u negative 4 over negative 4 plus c. Notice that the exponent could be positive and could be negative. Now the integral of 1 over x cubed dx. This cannot be found automatically, directly. So we have to translate this quotient into this form. It's easy, we just write the integral of 1 over x cubed dx as the integral of x to the power negative 3, which is x to the power negative 2 over 2 plus c. Now the integral of the square root of v dv, also we write it in this form. So this is v to the power half dv. We add 1 to the exponent and we divide by the sum. We get v to the power 3 over 2 over 3 over 2 plus c, which is 2v, the square root of v over 3 plus c after some simplification. Now the integral of 1 over x dx, if we apply the same property, this would be x to the power negative 1, which is x to the power 0 over 0, which is a very big problem. In fact, here we cannot apply this property because n in this specific case is negative 1, and this property is only applied when n is different from negative 1. Now let's talk about the Neperian logarithm. The function Neperian logarithm is the antiderivative of the function 1 over x. Means that it's the integral of 1 over x dx that is defined on 0 plus infinity, and it vanishes at 1. So f of 1 is 0. The Neperian logarithm is denoted by small l, small n, and it's read as ln. Now let's calculate using the calculator, but before you use the calculator, let me show you the ln button on the calculator. Let's say this is the calculator. Well, you see this is the ln button. If I want to find, for example, ln 5, I press on this button, ln, and then I write 5, I cross parentheses, and then I press on the equal sign to get 1.609, blah blah blah. Another example, if I want to calculate, let's say ln the square root of 8, don't forget to go outside the radical sign and then you close the parentheses, equal, we get 1.039. The third one, if I want to find a fraction that contains ln in the numerator, for example ln 8 divided by, let's say, another ln in the denominator, ln of 0.5, this would be negative 3. Now there's something else that I'd like to show you On the calculator also we have a new number which is called e. It's the exponential e. To find e, we press on alpha, and then on this button you see this very small letter here, which is small e. This is e, and it's about 2.7. E in fact is a constant which is about 2.7. It's like pi. You know pi, which is 3.14, which is also a constant. Now if I want to calculate, for instance, ln of e, this is e, close parenthesis, this is equal to 1. Okay, now let's go back to our activity. Please use your calculators to calculate ln 10. It will be 2.30. Calculate to the nearest 10 -2 means 2 decimal places. Ln 100 is 4.61. Ln 3 is 1.10. Ln 0.5, which is negative 0.69. Ln pi, which is 1.14. And then recalculate e. It will be 2.72, about 2.72. Ln e is 1. Ln e cubed is 3. Ln 1, which is 0. And ln 0.001 is negative 6.91. Now what is ln 0? Using the calculator, you're going to see that it gives a math error. Ln of negative 0.001 is also a math error. Ln of negative 1 is a math error. Ln of negative 4 is a math error. And ln of negative 10 is a math error. Now what can we deduce from this activity? Let's see. First, we have to know that ln 1 is 0 and e is a constant which is about 2.7, and ln e is 1. Now we can find ln 1 and ln e using the calculator, but because they are frequently used, it's better to memorize them. We can also see from this activity that ln x exists for x is positive, because when x is 0 or negative, as you see from this part of the activity, the calculator gave a math error. Now we can also see that ln x could be negative when x is between 0 and 1, like for example ln 0.5 and ln 0.001, and it's positive when x is greater than 1. So remember, ln x could be positive, could be negative, and could be 0, but x in this case should always be strictly positive. Now let's see this example. Answer by true or false. Ln 0 is 1. Is this true or false? In fact, this is false because ln 0 does not exist. Ln 3 is positive. This is true. We can use the calculator, or we can say that the 3 is greater than 1. Ln e is 1. This is also true. We memorized it. Ln 0.2 is positive. This is false because when x is between 0 and 1, the ln is negative. And ln 5 is smaller than ln e. You can here use the calculator. This is also false. Now complete by greater, equal, or smaller. Ln 10 and 1. You can use the calculator. Try to do it alone. You see that ln 10 is greater than 1. Ln 2/3 and 0. Well, ln 2/3 is less than 0 because 2/3 is between 0 and 1. Ln of 3/2 and 0. Ln 3/2 is greater than 0 because 3/2 is greater than 1. Ln e and 2. And ln 1 and 0. Ln 1 is equal to 0. Now let's see the algebraic properties of the Neperian logarithm. In other words, how can we deal the len function. Complete the table below using the calculator. Round the answer to the nearest hundredth, 10 to the power negative 2. Try to fill in this table. If a and b are two strictly positive real numbers and n belongs to z, we can see from here that len of ab from here is the same as len a plus len b. See? Len ab is the same as len a plus len b. And we can also see that len ab is not the same as len a times len b. Pay attention to this common mistake. We can also see that len of a over b, this is len of a over b, is the same as len a minus len b. You see, we get the same results. So len of a over b is the same as len a minus len b. And in fact, we can also see that len of a over b is not the same as len a over len b. You see, we have different results. And finally, we can also see that len a to the power 5 is, this is len a power 5, is nothing but 5 len a, which is somewhere here. So if we have an exponent here, we can put it outside the len expression, like this one. And also the common mistake, len a power 5 is not the same as len a to the power 5. So the results, the properties are len ab is len a plus len b, len a over b is len a minus len b, and len a power n is n len a, providing that a and b are strictly positive real numbers. So the list is becoming longer and longer. Okay. Now let a be a strictly positive real number. Verify that len of 1 over a is minus len a. Len 1 over a is len 1 minus len a, applying this property, the division, and we know that len 1 is 0, so this becomes minus len a. Or we can also write 1 over a as a to the power negative 1 using exponents and applying the last property. This negative 1 becomes outside as a negative sign. Okay, now we need to write each expression in the form of len a, where a is strictly positive. In other words, I want the expression to be written so that we just have one len only. Len 10 minus len 2. If we use this property, what is len 10 minus len 2? It will be len of 10 over 2, which is len 5. Now what is len 10 plus len 2? We can apply the first property. So in this case, it becomes len 20. Now what is 2 len 3 plus 3 len 2? Remember, we cannot apply this property unless we have 1 len a plus 1 len b. So to translate the addition into a multiplication, we must have 1 len a. In fact, here we have 2 len 3, so we have to get rid of this 2. How do we get rid of a number which is outside the len? It's very easy, we just put it as an exponent inside the len. So this becomes len of a 3 squared. The first one is len of a 3 squared, and the second one is len of 2 cubed. And this is len 9 plus len 8, which is len 72. Now, how do we write 1 plus len 10 in the form of len a? Using one len only. We have to do something here to get rid of this one. It's also easy because we know that 1 is len e, and if we write it as len e plus len 10, this is nothing but len of 10e. Finally, if I want to write 3 in the form of len a, you see that the 3 is 3 times 1, and 1 is replaced by len, and we remove this 3, we put it as an exponent, so it becomes len e cubed. In fact, we can use it directly, automatically. 3 is len e cubed. K is len e to the power k. Now, application. Write each expression in the form of p len 5 plus q len 2 plus r, where p, q, and r are real numbers. Now you need to write len 50 in this form. Try to do it alone. Remember the prime factorization method. So 50 could be written as 5 squared times 2, and this is len of 5 squared times 2, which is len of 5 squared plus len 2. And here we get rid of the exponent, we put it outside, this becomes 2 len 5 plus len 2. So this is of the form p len 5 plus q len 2 plus r, where r is 0. Now len of 100 radical e. Also try to do it alone. In fact, len of 100 radical e, this is len ab, could be written as len a plus len b, and len 100 is len of 2 squared times 5 squared, and radical e could be written as e to the power half. Using the properties, we get this expression, which is 2 len 2 plus 2 len 5 plus half. Now verify that len e power x is x for any x. This is very easy. Len e power x is x len e, which is x. Okay, Amir, Mira, or Rami? Who is saying the truth? Amir. Amir states that len of 5 plus 3 is len 5 times len 3. Mira is saying that len of 5 times 3 is len 5 plus len 3. And Rami is saying that len of 5 plus 3 is len 5 plus len 3. Now, which one of the three students is saying the truth? In fact, the len translates the product into a sum. So Mira is saying the truth.